Hi, thanks for coming to my talk. I'm Ziyi from NUS, and this talk is about synthesizing inductive heap predicates. So it's joint works with my advisor, Ilya. So separation logic. A lot of people like it, but just to give basic background, it's a program logic to reason about program heaps. For example, here we have x points to y and y points to x. And different from classic logic, the star here is called separating conjunction, which is about these two assertions is to be not overlapping in the sense that x points to y and y points to x are separately. So it's something widely used in a lot of domains. A very useful feature in separation logic is the predicates. When you want to reason about the data structure, then you need to use the predicate to express the data structure. Here's an example of singly linked list. And the base case is about the list is empty. And the inductive case is about we have a pointer j such that I points to the value a and j. And separating conjunctive is another recursive occurrence of the list. So other than the spatial part expressing the heap, we have the pure parts as the blue ones to describe some data payload. So although it's pretty expressive, but the expressiveness also come up with the difficulty, the complexity of this thing. So for example, you want to express doubly linked list segment. You are having the separating conjunction together with complex recursion, and you need to have 4 pointers as the arguments to express this predicate. Another example is nested data structure as list of cyclic list. It's not very intuitive about how to express that thing. And different systems are having different dialect of separation logic predicate to describe the payload. So overall, we find specifying separation logic predicate is difficult. We want to make it easier. And intuitively, examples can be more easy to come up with compared to the formal definitions. And what is the example here? It's the instance of the data structure. Like here we have the heap memory graph. On the right is describing a binary search tree. And what we want is to have a set of such memory graph to synthesize the corresponding formal definition of the separation logic predicate. So our task in general is to synthesize the predicate, and we want to have first effective method, and then to make it efficient. If you have heard of inductive logic programming, you might think it's quite relevant. So the problem setting here is giving positive and negative examples of the predicate and learn an optimal predicate that makes all of the positive instance provable and all of the negative one unprovable. For example, we have 5 positive, 5 negative examples here, and we find the predicate can be learned by the state-of-the-art ILP system that is filtering out all of the odd number in the list. But what's the problem here is in ILP, you need to have negative examples, but in general, when we think about the data structure, we are thinking about the positive one. So we want to first figure out what happens and why we need the negative in the traditional setting. See, we want to learn sorted list, which is essentially singly linked list, but with the min set restriction saying that it is sorted. By giving the 2 positive examples on the left, what we learn from the existing ILP system is actually the version without the min set constraint is essentially singly linked list. So what's the problem here? Is there anything wrong? Nothing is going wrong because any sorted list is also a singly linked list. So the functionality of negative examples is actually about not to make the result too general. Here's the illustration. If we have 2 positive examples, the most general one can be too general. So the traditional setting uses negative examples. But we think about if we only have the positive example, it is also a case that we can learn the most sophisticated one that can be meaningful. Here's another gap. let's see, we want to think about the shortest in-size is the most general hypothesis, is a good approximation. But for the most specific one, the largest in-size is not a good approximation, because thinking about F1 and F2 here, F2 is longer than F1, and it has an extra assertion saying A is greater than B. But it makes no sense because it has been entailed by A is equivalent to B plus 1. So to make positive online learning work, we first need to normalize the search space. That is, in our case, by logic normalization, to get rid of such case and to learn the most specific hypothesis by positive online learning. Visit, and we have the example input, and we learn what we want. So is it currently be effective? It's not the case, because ILP learns per log program, and we are having separate logic predicate. To illustrate the gap here, we have another example on the left. We want to learn the predicate P from the graph on the left. But thinking about another predicate, the later one is actually also working in a per log program, because you see, by replacing B with C and have two occurrences of P, then nothing goes wrong in per log. But it's not following the separating conjunction. So that's gap, and we want to resolve this problem as, if you are familiar with separating logic, the later predicate is actually a binary tree, but it's not working at all. So as hinted by the title, we solve this problem by heap linearity, in the sense that for all of the facts describing this memory graph, we can only use it once during the per log proof to check the validity of separating logic. So only if it used once, then we can guarantee that it's within the separating conjunction semantics. So now it's being effective. Now we deal with efficiency. Actually, the previous one is about the semantics of separating logic. And here we also have different semantics can be used to prune the search space. For example, if the pointer is no pointer, we cannot use the n-ary and something like heap functionality. So this semantics-based pruning are achieved by answer-step programming. Here we're basically saying that if a variable is no pointer, then it can only appear in the rule for twice. So our tool CP is a combination of traditional inductive logic programming plus positive online learning and a lot of separate logic domain. The user can specify the memory graph by manually written or get it from some programs, and we synthesize and output the heap predicate for further use. Here's our main result. We synthesize a branch of predicate, and most of them are out of the capability of existing work. Here's an example. So row tree is actually very complex because there are some mutual recursion in the predicate, but in ILP we can deal with it. We have more discussion in the paper about the negative examples, about the formal definition stuff, and also have an illustration on the different application scenario. Now the story of separating logic stops here, and I want to give another aspect of the tool, which is about synthesis. So we use answer-step programming, which is essentially logic programming combined with satisfiability solving. And we are now the first one to use ASP to do the synthesis. Here's a list, recent list, but we also don't want to be the last one to use ASP to do the synthesis. So here's the secret. What happened to the system is about defining the search space as a set. For example, all of the possible inductive heap predicate as a search space, and the pruning as the set operations. They can be modeled by ASP encoding. And then there are a well-tuned solver. You can use it with a lot of useful feature for your enumeration in the enumeration-based synthesis. So if you are interested in details of the connection between synthesis and ASP, or you care about the domain in first-order formula, please check out our latest paper. To wrap up, to do is the synthesizing separate logic. We propose positive online learning to make it work, and we have linearity to fill the gap between separate logic and logic programming. Then the semantics-based learning make it efficient. So overall, we have a synthesizer and can be used in different separate logic-based tools. That's all. Thanks.
Any question from the audience? Yeah, maybe, I start from the first question. Since this is a positive only learning, do you observe in any case in your evaluation that the learned predicate is not the strongest one?
The strongest is defined in certain cases. So in general, the strongest one is the conjunction of all of the input examples. Yeah. But here, because we can restrict the shape of the predicate to be not that specific, so it has to be within the shape of inductive heap predicate, separate logic predicate. So, but after that setting, it can overfit, but it's always the strongest one.
But you have this you have a theoretical guarantee that the result is the strongest, right?
Within certain restrictions. So, for example, we have a predicate with certain size, and we can guarantee that in a larger size, there's no such more specific one, but it's not infinite.
Okay, thanks.
Hi, thanks for the talk. Actually, to follow up on that, the positive-only learning is kind of dependent on the fact that your constructs aren't going to in any way form anything like a disjunction, right?
Right.
The minute you have a disjunction, you're immediately going to overfit way too much. Isn't separation logic a domain where you kind of risk that? Like, I mean, I'm impressed that this works, and I know that this works. But how did you finesse that into working?
So overfitting is in general anywhere in example-based synthesis, and at least in this work, given the certain domain, it is okay for not to get rid of overfitting, but yeah, it's in general unavoidable. If the quality of example is not that good, then you result in something you didn't expect it. So yeah, it depends on the input. It's actually the overall problem of example-based synthesis.